Watch the dates. In 1977, NASA launched a spacecraft weighing 825 kilograms on a trajectory toward Jupiter. 12 years later, that same spacecraft had visited 4 planets, crossed 4.5 billion kilometers, and was heading out of the solar system at roughly 17 kilometers per second. It did not carry enough fuel to do any of that. The engine that carried Voyager 2 past Jupiter, Saturn, Uranus, and Neptune was not on board the spacecraft. It was the planets themselves. The space economy runs on money, as the last video showed, and nearly all of it flows into infrastructure nobody sees. But there is a resource in space that costs nothing, weighs nothing, and cannot be depleted: gravity. The trick is knowing when to use it, and the window for the shot Voyager took will not open again for roughly 175 years. A gravity assist is deceptively simple in concept. A spacecraft approaches a planet. The planet's gravity accelerates the spacecraft as it falls toward it. The spacecraft swings behind the planet and climbs away on the other side. From the planet's perspective, nothing unusual happened. The spacecraft arrived at a certain speed, curved around, and departed at the same speed. The encounter is symmetric. No energy was gained or lost relative to the planet. But from the Sun's perspective, the picture is different. The planet is moving. It is orbiting the Sun at tens of kilometers per second. By swinging behind a moving planet, the spacecraft picks up a fraction of that orbital velocity. The gain is real. The spacecraft leaves the encounter moving faster relative to the Sun than when it arrived. The planet, in exchange, slows down by a corresponding amount. But Jupiter masses roughly 2 times 10 to the 27th kilograms, and the spacecraft masses 825. The change in Jupiter's orbital velocity from a Voyager flyby is on the order of 10 to the negative 24th kilometers per second. Undetectable. The spacecraft, meanwhile, gained about 10 kilometers per second. The analogy that gets used most often is a tennis ball thrown at a moving freight train. The ball bounces back faster than it arrived. The train does not notice. The physics had been understood in pieces for decades. Kondratyuk described the idea of using planetary gravity for trajectory changes as early as 1918. Zander made a similar argument in 1925. The Soviet probe Luna 3 used the Moon's gravity to photograph its far side in 1959. But none of these investigators made the full connection. They saw that gravity could bend a trajectory. They did not see that gravity could propel a spacecraft from planet to planet across the entire solar system, replacing fuel with geometry. That connection was made in the summer of 1961 by a graduate student named Michael Minovich. He was working at JPL on a summer assignment, tasked with solving a trajectory problem involving conic sections in the Sun's gravitational field. Minovich realized that by converting between planet-centered and sun-centered reference frames, he could compute the velocity change a spacecraft would experience during a close planetary flyby. He used the fastest computer available at the time, an IBM 7090, to run simulations of the three-body problem. His results, submitted in a 41-page technical memo on August 23, 1961, showed that a spacecraft could gain enough velocity from a single Jupiter flyby to reach the outer planets. The paper was typed on a typewriter. The diagrams were drawn by hand. The Greek symbols were written in by pen, and the idea inside it would make every major interplanetary mission of the next 6 decades possible. Hale finds gravity assists genuinely beautiful, and that is not a word that comes up often on this channel. Not the physics alone, which is elegant but not unique. The beauty is in the constraint. The maneuver works only if the spacecraft arrives at precisely the right point in space at precisely the right moment. The geometry must be exact, the timing must be exact, and the planets, obviously, do not adjust their orbits to accommodate a launch schedule. The mission designer works backward from a desired trajectory, finds the window, and launches into it. If the window is missed, the next one may be years away, or decades, or in the case of Voyager, nearly 2 centuries. 3 years after Minovich's memo, another summer student at JPL made a discovery that turned the mathematics into a mission. Gary Flandreau was assigned to study trajectories to the outer planets. He plotted the positions of Jupiter, Saturn, Uranus, and Neptune across several decades and noticed something. In the late 1970s, all 4 planets would be arranged in a loose arc on the same side of the Sun, each positioned so that a gravity assist at one would send a spacecraft toward the next. Flandreau called this the Grand Tour. The alignment occurs once every 175 years. The previous one had been in the early 1800s, when the fastest transportation on Earth was a horse. The next will be around 2150. When Flandreau presented the idea to senior engineers at JPL, the response was skepticism. They did not believe the mission was feasible. He published his results in 1966. NASA initially planned a billion-dollar grand tour with 4 spacecraft. Congress canceled it in 1971 under budget pressure from the shuttle program. What survived was a scaled-down version, 2 spacecraft, advertised as missions to Jupiter and Saturn only, built with enough capability to continue to Uranus and Neptune if the first probe succeeded. The project was renamed Voyager. Voyager 2 launched on August 20, 1977. Its first gravity assist came at Jupiter on July 9, 1979. The spacecraft approached from behind the planet in its orbit and passed within 570,000 kilometers of Jupiter's cloud tops. Before the encounter, Voyager 2's heliocentric velocity was roughly 10 kilometers per second. After the flyby, it was roughly 20. Jupiter had effectively doubled the spacecraft's speed. That single maneuver lifted Voyager 2's velocity above the solar escape threshold, meaning it now had enough energy to leave the solar system entirely, with or without further assists. But the trajectory was aimed at Saturn, not at the exit. At Saturn, Voyager 2 executed a tight turn, passing close enough to use the planet's gravity to redirect its path sharply out of the plane of the ecliptic and toward Uranus. This was the critical maneuver. Jupiter's assist was large and relatively forgiving in terms of aim. Saturn's was smaller and demanded higher precision because the geometry required to reach Uranus was narrow. The navigators at JPL had to thread the spacecraft through a specific corridor above Saturn's rings, close enough to bend the trajectory by the required angle, far enough to avoid the ring debris. The corridor was roughly the width of a large city, at a distance of over 1 billion kilometers. At Uranus, the gain was smaller again, and the flyby redirected Voyager 2 toward Neptune. At Neptune, in August 1989, Voyager 2 passed within 5,000 kilometers of the planet's cloud tops, the closest approach of the entire mission. The spacecraft was traveling at roughly 27 kilometers per second relative to Neptune. It flew over Neptune's north pole and was deflected sharply southward, passing close to the moon Triton on its way out. 12 years, 4 planets, 4 gravity assists. The total velocity gained from planetary flybys was greater than the velocity provided by the launch vehicle itself. Voyager's rocket got it off Earth. The planets got it across the solar system. The technique did not end with Voyager. Cassini, launched in 1997 to study Saturn, used 4 gravity assists from 3 different planets, 2 from Venus, 1 from Earth, 1 from Jupiter. Each flyby bent the trajectory and added velocity, building up enough energy over 7 years to reach Saturn's orbit. Once there, Cassini performed 127 close flybys of Saturn's moon Titan, each one a smaller gravity assist that reshaped its orbit around the planet. Galileo, launched in 1989, needed 3 assists, 1 from Venus and 2 from Earth, just to reach Jupiter, because its original high-energy booster had been canceled after the Challenger disaster and replaced with a weaker solid rocket that could not deliver the spacecraft directly. New Horizons used a single Jupiter assist in 2007 to gain an additional 14,000 kilometers per hour on its way to Pluto, cutting 3 years off the journey. There is a pattern here that matters beyond the engineering. Every one of these missions was shaped not by what the spacecraft could carry, but by what was already in the solar system, moving on its own schedule. The fuel budget that determines how far a spacecraft can go is called delta V, and for most missions, the delta V budget is the single hardest constraint. Gravity assists expand that budget by borrowing velocity from objects that have it in abundance. The cost is 0. The constraint is time. A mission designer cannot choose when Jupiter is in the right position. Jupiter does not accelerate or slow down on request. The window opens and the window closes, and the physics does not negotiate. Consider what would have happened without the Grand Tour alignment. Voyager 2 launched in 1977 with a velocity of roughly 36,000 kilometers per hour relative to Earth. Without any gravity assists, a spacecraft traveling at that speed toward Neptune would take over 30 years to arrive, depending on the trajectory. Voyager 2 did it in 12. The 3 decades saved are not an engineering improvement. They are a gift from planetary geometry, available only to those who know when to reach for it. Flandreau saw the window in 1964 because he was plotting planetary positions by hand and noticed a pattern that the computers of the day were not programmed to look for. That is the deeper point. The solar system is a machine. Its gears are planets, orbiting on schedules set by gravity and initial conditions 4.5 billion years ago. A gravity assist is not a trick. It is a recognition that the machine has moving parts, and that those parts can do work on your behalf if you time your arrival correctly. The spacecraft does not fight the system. It uses it, and the precision required, threading a corridor the width of a city at a distance of 1 billion kilometers, using instruments from the 1970s on a 41-page theory typed on a typewriter, is the kind of engineering achievement that does not announce itself with explosions or press conferences. It announces itself with a signal from Neptune, arriving at the speed of light 4 hours after the spacecraft has already moved on. The elegance of a gravity assist is that it solves the hardest problem in space travel, distance, without solving it the way engineers usually do, by adding more engine. It solves it by reading the geometry of what already exists and arriving at the right place at the right time. That constraint, the timing, is also why it cannot be repeated on demand. The window for the Grand Tour closed in the early 1980s. It will not reopen until the middle of the 22nd century. Every outer planet mission launched between now and then will use single-planet assists, not the 4-planet chain that Voyager flew. The shot was taken, the data was collected, and the alignment is gone. Gravity assists are the most elegant solution to distance that physics allows. But between Earth and Mars, the distance is not the hardest problem. The hardest problem is what fills that distance, a radiation field composed of galactic cosmic rays that no existing material can fully stop, and solar particle events that arrive without warning. For that problem, there is no elegant solution. There are only trade-offs.